Picture this: a black hole, born in the universe's first moments, silently drifting through space until it collides with a dying star. Unlike ordinary black holes, this one didn't form from a collapsing star, it's a primordial relic, forged in the chaotic infancy of the cosmos. Now, imagine it sinking into a white dwarf, siphoning mass until the star's core implodes in a cataclysmic explosion, brighter than a billion suns. But here's the mind-blowing part: this explosion wouldn't just be a stellar death knell, it would leave behind a chemical fingerprint, a unique signature in the supernova's light that could reveal the black hole's presence. Astronomers are now hunting for this telltale blow, hoping to catch a glimpse of these ancient, invisible giants. If they're right, it's not just a new way to explain supernovae, it's a chance to peer back to the universe's earliest days, hidden in the ashes of stellar explosions. In the vast tapestry of the universe, some of the most mysterious phenomena are still waiting to be unraveled. Recently, astronomers have uncovered a fascinating possibility: primordial black holes, hypothetical remnants from the universe's earliest moments, could be the hidden architects of type Ia supernovae. These cosmic explosions, long thought to be the result of white dwarf secreting material, might instead have a more enigmatic origin. This discovery challenges our understanding of stellar evolution and opens a new window into the universe's hidden structures. Let me explain how this could be possible. To grasp this idea, we first need to revisit what we know about black holes. Most black holes are the remnants of massive stars that collapsed under their own gravity at the end of their lives. But there's another class of black holes, primordial black holes, that scientists have long speculated about. Unlike their stellar counterparts, primordial black holes are thought to have formed in the first fractions of a second after the Big Bang. At that time, the universe was an extremely hot, dense soup of subatomic particles. In some theoretical scenarios, tiny pockets of this matter could have collapsed under their own gravity, creating black holes with masses ranging from microscopic to potentially hundreds of times that of the Sun. These primordial black holes, if they exist, would be vastly different from the black holes we observe today. They wouldn't have formed from stars, and their existence would be a direct consequence of the universe's early conditions. Now, the new research suggests that these elusive primordial black holes might not just linger in the cosmos, they could actively interact with other celestial objects. Specifically, scientists are exploring how primordial black holes might encounter white dwarfs. White dwarfs are the dense, Earth-sized remnants of stars that have exhausted their nuclear fuel. They are incredibly compact, with masses comparable to the Sun but packed into a volume smaller than Earth. These objects are known to be unstable when they accumulate mass beyond a critical threshold, leading to a runaway nuclear reaction that culminates in a type Ia supernova. But what if this process isn't entirely driven by the white dwarf itself? What if an external factor, something as strange as a primordial black hole, could tip the scales? The key insight here is that primordial black holes, due to their small size and high density, could potentially drift into a white dwarf. Imagine a scenario where a primordial black hole, perhaps no larger than a grain of sand, slowly migrates toward a white dwarf over millions of years. As it approaches, the intense gravitational pull of the white dwarf would begin to slow the black hole's motion. This interaction could lead to a gradual transfer of mass from the white dwarf to the black hole. Over time, this process might cause the white dwarf to accumulate enough material to trigger a catastrophic explosion, a type Ia supernova. However, this isn't a simple transfer of mass. The black hole's presence would alter the white dwarf's internal structure, potentially creating conditions that lead to the explosion in a way that differs from the traditional model of accretion from a companion star. What makes this scenario particularly intriguing is the potential for unique chemical signatures in the resulting supernova. Type Ia supernovae are famous for their uniform brightness, which has made them valuable tools for measuring cosmic distances. However, this new research suggests that if primordial black holes are involved, the explosions might leave behind distinct chemical fingerprints. These could include unusual isotopic ratios or the presence of elements that don't typically form in the standard white dwarf accretion model. By analyzing the light emitted during these explosions, astronomers might be able to detect these anomalies, which would serve as a smoking gun for the involvement of primordial black holes. This would be a groundbreaking discovery, as it would provide direct evidence for the existence of these ancient, enigmatic objects. But how can we be sure this is more than just theoretical speculation? The researchers behind this study have proposed a way to test this hypothesis. They suggest that by studying the remnants of type Ia supernovae, astronomers could look for specific patterns in the debris left behind. For example, the presence of certain heavy elements or the distribution of radioactive isotopes might indicate a different mechanism of explosion. Additionally, the way the supernova's light curves, how its brightness changes over time, could differ from the standard model if primordial black holes were involved. These deviations, if detected, would not only confirm the role of primordial black holes but also offer clues about their properties, such as their mass and spin. It's important to note that this research doesn't claim to have definitively proven the existence of primordial black holes. Instead, it presents a compelling scenario that could explain some of the observed characteristics of type Ia supernovae. The fact that these explosions remain one of the most studied phenomena in astrophysics means that any new theory must align with existing data while also offering fresh insights. The idea that primordial black holes could be responsible for some of these explosions adds a new layer of complexity to our understanding of stellar death and the universe's hidden structures. For decades, type Ia supernovae have been a cornerstone of cosmology, helping scientists measure the expansion rate of the universe. Their consistent brightness has allowed astronomers to track how the universe's expansion has changed over time, leading to the discovery of dark energy. If primordial black holes are indeed involved in some of these explosions, it could mean that our current models of these events are incomplete. This possibility raises exciting questions about the role of dark matter and other mysterious components of the universe. After all, primordial black holes are one of the few theoretical candidates for dark matter, and if they can trigger supernovae, their influence might extend far beyond what we've previously imagined. The implications of this research go beyond the study of supernovae. If primordial black holes are confirmed to exist and interact with white dwarfs in this way, it would open new avenues for exploring the early universe. These black holes, formed in the first moments after the Big Bang, could provide a unique window into the physics of the cosmos during its infancy. Their interactions with other objects might reveal details about the distribution of matter in the early universe, offering insights into how structures like galaxies and clusters formed. Moreover, the ability to detect these black holes through their association with supernovae could provide a new method for locating them, which has been one of the biggest challenges in astrophysics. Of course, there are still many unanswered questions. For instance, how common are primordial black holes, and what are their exact properties? How do they navigate through the cosmos to encounter white dwarfs? And what are the precise mechanisms by which they trigger supernovae? These questions highlight the speculative nature of the research, but they also underscore the importance of continued exploration. The scientific community is already working on ways to refine the models and gather more data. Future observations of supernovae, combined with advancements in computational simulations, could help bridge the gap between theory and observation. In the grand narrative of the universe, primordial black holes represent a tantalizing mystery. They are a reminder that the cosmos is filled with phenomena that challenge our understanding and push the boundaries of science. The possibility that these ancient, invisible objects could be responsible for some of the most dramatic events in the universe is a testament to the power of curiosity and the relentless pursuit of knowledge. As we continue to look deeper into the cosmos, discoveries like these remind us that the universe is still full of surprises and that our quest to understand it is far from over. Primordial black holes, PBH, remain hypothetical, but that isn't stopping astrophysicists from figuring out how they could interact with other stellar objects. New research shows how PBHs, formed in the early universe from collapsing pockets of dense subatomic matter instead of from stars, can enter white dwarfs. In some cases, that could have triggered a type Ia supernova with particular chemical fingerprints, which should be detectable. This part of our deep dive into primordial black holes can trigger type Ia supernovae, and astronomers should be able to find them focuses on, walk through how scientists found or confirmed this instruments, telescopes, missions, method, timeline. Make the process itself feel impressive. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Primordial black holes, PBH, remain hypothetical, but that isn't stopping astrophysicists from figuring out how they could interact with other stellar objects. New research shows how PBHs, formed in the early universe from collapsing pockets of dense subatomic matter instead of from stars, can enter white dwarfs. In some cases, that could have triggered a type Ia supernova with particular chemical fingerprints, which should be detectable. This part of our deep dive into primordial black holes can trigger type Ia supernovae, and astronomers should be able to find them. Focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, astronomers have puzzled over the mysterious explosions known as type Ia supernovae. These cosmic fireworks, which outshine entire galaxies for brief moments, have long been considered standard candles in the universe, tools that helped reveal the accelerating expansion of the cosmos. But the exact mechanisms that trigger these explosions have remained a subject of intense debate. In the 1970s, the prevailing theory was that type Ia supernovae result from white dwarf stars, the dense remnants of once massive stars, accreting material from companion stars until they reach a critical mass. This model, based on the work of Subramanian Chandrasekhar, suggested that the explosion occurs when the white dwarf approaches the Chandrasekhar limit, about 1.4 times the mass of the Sun. However, this theory faced challenges. Observations showed that the explosions were remarkably uniform in brightness, yet the details of how white dwarfs could consistently reach that precise mass threshold without disrupting their companions remained unclear. Over time, scientists realized that the traditional model might not account for all scenarios, especially as new data emerged about the universe's accelerating expansion. In the 1990s, observations of distant supernovae revealed that the universe's expansion was speeding up, a discovery that earned the 2011 Nobel Prize in Physics. This finding was made possible by measuring the brightness of type Ia supernovae as standard candles, but it also raised questions about the reliability of these explosions as cosmic yardsticks. If type Ia supernovae were not as uniform as once believed, their use in measuring cosmic distances could be flawed. This discrepancy spurred a search for alternative explanations, including the possibility that different physical processes might be responsible for these explosions. Around the same time, the search for dark matter intensified. While dark matter remains elusive, Some theories suggested that primordial black holes, hypothetical objects formed in the early universe from dense pockets of matter, could serve as dark matter candidates. These black holes, if they exist, would be much smaller than stellar mass black holes and could have formed in the first moments after the Big Bang. Unlike the black holes we observe today, which form from the collapse of massive stars, primordial black holes would have a different origin. Their existence was never confirmed, but their potential to interact with other cosmic objects sparked new avenues of research. In the 2010s, a breakthrough came when scientists began to explore how primordial black holes might influence stellar evolution. Simulations suggested that if a primordial black hole were to drift into a white dwarf, it could trigger a type Ia supernova. This idea built on earlier work that considered the role of neutron stars or other compact objects in such scenarios, but the unique properties of primordial black holes, such as their small size and potential abundance, made them an intriguing possibility. The key insight was that a primordial black hole, if it entered a white dwarf, could merge with the star's core, disrupting its equilibrium and initiating a runaway nuclear reaction. This process would differ from the traditional accretion model, which relies on gradual material transfer from a companion star. The idea that primordial black holes could act as triggers for type Ia supernovae gained traction as researchers sought to reconcile the observed uniformity of these explosions with the complexities of stellar physics. At the same time, advances in observational astronomy provided new tools to test these hypotheses. High-resolution spectroscopy, for example, allowed scientists to analyze the chemical fingerprints of supernova remnants, searching for signatures that might indicate a different explosion mechanism. If primordial black holes were involved, the resulting supernovae might leave behind unique isotopic patterns or elemental abundances that distinguish them from traditional type Ia events. This line of inquiry also connected to the broader search for dark matter. If primordial black holes could account for some of the missing mass in the universe, their detection might not require direct imaging but rather indirect evidence from their interactions with other objects. Theoretical models began to explore how these black holes could accumulate in regions of space, potentially influencing the formation of galaxies or the distribution of matter. However, the challenge remained: how could astronomers confirm the existence of primordial black holes if they didn't emit light? The answer, it seemed, lay in their interactions with visible matter. If a primordial black hole entered a white dwarf, the resulting explosion would produce detectable light, offering a way to observe these elusive objects indirectly. This idea brought together two long-standing mysteries: the nature of type Ia supernovae and the identity of dark matter. By the 2020s, simulations had become more sophisticated, allowing researchers to model the dynamics of primordial black holes merging with white dwarfs in greater detail. These models suggested that such collisions could occur under specific conditions, such as when a white dwarf is in a binary system or when the black hole's trajectory is influenced by gravitational interactions. The resulting supernovae might exhibit subtle differences in their light curves or spectral features compared to traditional type Ia events, providing a potential signature for detection. This research also highlighted the importance of multi-wavelength observations, as different wavelengths could reveal distinct aspects of the explosion. For example, X-ray or gamma-ray emissions might indicate the presence of a primordial black hole, while optical and ultraviolet data could capture the unique chemical signatures left behind. The implications of this work extended beyond supernova studies. If primordial black holes could trigger type Ia supernovae, their existence would reshape our understanding of cosmic evolution. They might have played a role in seeding the universe's structure or influencing the formation of other stellar objects. Moreover, their potential connection to dark matter suggested that the search for these black holes could yield insights into one of the greatest mysteries of modern physics. Yet, despite these promising developments, the question of whether primordial black holes actually exist remains open. While the theoretical framework has grown stronger, observational evidence is still lacking. The search continues, driven by the possibility that these ancient relics of the early universe could hold the key to unlocking new cosmic phenomena. As astronomers refine their models and improve their observational techniques, the prospect of detecting primordial black holes and the supernovae they might trigger remains a tantalizing frontier in the exploration of the cosmos. The idea that primordial black holes could trigger type Ia supernovae is still in its early stages, and there are plenty of questions that remain unanswered. For starters, we don't yet know for sure whether primordial black holes even exist. While they're a popular theoretical concept, there's no direct evidence to confirm their presence. Most of what we know about them comes from models and simulations, not from observations. This uncertainty means that any discussion about how they might interact with white dwarfs or trigger supernovae is still speculative. Scientists are still debating whether these hypothetical objects could have formed in the early universe, and if so, how they might have evolved over billions of years. Some researchers argue that the extreme density of the early universe could have created pockets of matter so massive that they collapsed into black holes almost instantly. Others suggest that these objects might have formed through different mechanisms, such as quantum fluctuations or phase transitions in the primordial plasma. Without more data, it's hard to say which theory is correct, and this lack of consensus is one of the biggest mysteries surrounding primordial black holes. Even if they do exist, there's another question: how would they interact with white dwarfs in the first place? The idea that a black hole could merge with a white dwarf and trigger a supernova is fascinating, but it raises a lot of unresolved issues. For example, how would a primordial black hole even find its way into a white dwarf? White dwarfs are dense, compact stars that have already shed their outer layers, so they're not the kind of objects that would naturally attract a black hole. Some researchers propose that the black hole might have been captured by the white dwarf's gravitational field, but the exact mechanics of this process are still unclear. Another challenge is understanding the timescale of such an interaction. If a black hole were to merge with a white dwarf, how long would it take for the resulting explosion to occur? And what would the explosion look like? Type Ia supernovae are known for their uniform brightness, which makes them useful as cosmic mileposts, but if some of them are caused by primordial black holes, their chemical signatures might differ from the standard model. This could mean that we might need to revise our understanding of how these supernovae form and what they tell us about the universe. However, detecting these differences is easier said than done. The chemical fingerprints left behind by a primordial black hole-induced supernova would have to be subtle enough to stand out from the usual signatures of other supernova types. For instance, the presence of certain isotopes or elements could indicate a different mechanism at play. But how would astronomers even know what to look for? This is where the debate really heats up. Some scientists argue that the unique conditions created by a black hole merging with a white dwarf could produce specific elemental abundances that are distinct from those seen in other supernovae. Others are skeptical, pointing out that we've only observed a handful of Type Ia supernovae in detail, and it's possible that the variations we see could be explained by other factors. The challenge here is not just identifying the right signatures but also ensuring that we're looking at the right kind of supernovae in the first place. Even if we could detect these chemical fingerprints, there's another layer of complexity: how often would such events actually occur? If primordial black holes are rare, then the number of Type Ia supernovae they could trigger would be limited. But if they're more common, then we might expect to see more of these events. However, we don't yet have a clear picture of how many primordial black holes might exist in the universe, or where they might be located. Some researchers suggest that these objects could be concentrated in certain regions of space, such as near the centers of galaxies or in dense star clusters. Others argue that they might be spread out more evenly. Without knowing their distribution, it's hard to predict how frequently they might interact with white dwarfs. This uncertainty also affects how we might go about searching for them. If we're looking for evidence of primordial black holes, we'd need to design our observations carefully. For example, if a Type Ia supernova shows signs of being caused by a black hole merger, we might look for specific patterns in its light curve or spectral data. But even if we find such a signal, we'd still need to rule out other explanations. This is a classic problem in astronomy, distinguishing between different possible causes for the same observational evidence. The search for primordial black holes is also complicated by the fact that they're incredibly small. If they're as massive as the Earth, they'd be about the size of a grain of sand, but if they're smaller, they'd be even tinier. Detecting such small objects is a huge challenge, especially since they wouldn't emit any light on their own. Instead, we'd have to look for indirect signs, like the gravitational effects they might have on nearby stars or the way they interact with other matter. This is where the idea of using Type Ia supernovae as a clue becomes so intriguing. If we can find a way to link certain supernovae to primordial black holes, it could be a breakthrough. But it's also a long shot. The fact that we're even considering this possibility highlights how much we still don't know about the universe. Even if we could confirm that primordial black holes can trigger type Ia supernovae, there are still many unanswered questions. For example, what role do these objects play in the larger picture of cosmic evolution? If they're a significant source of dark matter, how would that affect our understanding of the universe's structure and expansion? And if they're responsible for some of the most energetic explosions in the cosmos, how does that change our view of stellar death and rebirth? These are all big questions, and they're part of what makes this topic so fascinating. The search for primordial black holes is not just about finding new objects, it's about rethinking some of the fundamental assumptions we have about how the universe works. It's a reminder that science is an ongoing process, where each discovery opens up new mysteries. And in the case of primordial black holes, those mysteries are as compelling as ever. Primordial black holes, PBH, remain hypothetical, but that isn't stopping astrophysicists from figuring out how they could interact with other stellar objects. New research shows how PBHs, formed in the early universe from collapsing pockets of dense subatomic matter instead of from stars, can enter white dwarfs. In some cases, that could have triggered a type Ia supernova with particular chemical fingerprints, which should be detectable. This part of our deep dive into primordial black holes can trigger type Ia supernovae, and astronomers should be able to find them focuses on, explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, astronomers have puzzled over the mysterious brightness of type Ia supernovae, those explosive stellar deaths that serve as cosmic lighthouses for measuring the universe's expansion. But what if these explosions aren't just the result of a star's final breath, but the work of something far stranger? Recent research suggests that primordial black holes, hypothetical relics from the universe's earliest moments, might be the hidden architects of some of these cosmic fireworks. These black holes, born not from collapsing stars but from dense pockets of matter in the universe's infancy, could be sneaking into white dwarfs, the dense remnants of sun-like stars, and triggering explosions with signatures unlike anything seen before. If this is true, it could revolutionize how we hunt for these ancient objects and even reshape our understanding of dark matter. Let me explain. Primordial black holes are a theory, not a confirmed discovery. Unlike the black holes we've observed forming from dying stars, PBHs are thought to have emerged in the first fraction of a second after the Big Bang. Imagine the universe as a seething cauldron of energy and matter, and in some regions, gravity clumped together so fiercely that it collapsed into a black hole before stars ever had a chance to form. These tiny, ancient objects could range in mass from a grain of dust to hundreds of times the sun's weight. While we haven't found any yet, their existence remains a tantalizing possibility because if they exist, they might hold answers to some of astronomy's biggest questions. Now, here's where things get even more intriguing. Some PBHs, particularly the smaller ones, might not stay isolated for long. They could wander through space, drawn by the gravitational pull of nearby stars. White dwarfs, those dense, Earth-sized remnants of stars that have burned through their fuel, are especially interesting targets. If a PBH drifts too close to a white dwarf, it could get trapped in the star's gravity well. Over time, the black hole's relentless pull would siphon material from the white dwarf, creating a swirling accretion disk. But here's the twist: as the black hole grows, it might trigger a runaway fusion reaction in the white dwarf's core. This could lead to a catastrophic explosion, a type Ia supernova. And this isn't just any supernova. The unique way the black hole interacts with the white dwarf might leave behind a distinct chemical fingerprint in the explosion's light, something astronomers could spot with the right instruments. This idea is still in its early stages, but it's already sparking excitement. If PBHs are indeed responsible for some type Ia supernovae, it could mean we're looking in the wrong places for dark matter. After all, PBHs are one of the few theoretical candidates for dark matter, and if they're hiding in white dwarfs, their presence might be betrayed by the explosions they trigger. Moreover, the chemical signatures of these supernovae could act as a cosmic map, guiding astronomers to regions where PBHs might lurk. It's a bold hypothesis, but one rooted in the physics we already know. The key is that these explosions wouldn't look like typical type Ia events. Their light curves, the way their brightness changes over time, might show unusual patterns, or their spectral signatures could reveal elements formed under extreme conditions. If we can detect these anomalies, it could be the first direct evidence of primordial black holes and a major leap in our understanding of the universe's hidden architecture. But let's be clear, this isn't just about finding black holes. It's about rethinking how stars die and how the universe evolves. Type Ia supernovae have long been our standard candles for measuring cosmic distances, but if some of them are powered by PBHs, we might be missing pieces of the puzzle. Imagine a universe where these explosions are not just cosmic beacons but also cosmic laboratories, revealing secrets about the early universe and the nature of gravity itself. And if we're right, the next generation of telescopes, those powerful, sensitive instruments peering into the cosmos, could be our guides in this search. They might not only find PBHs but also rewrite the story of how stars meet their end. So, what does this mean for us? It means the universe is full of surprises, and our tools are only beginning to grasp its complexity. If you've enjoyed this deep dive into the cosmic dance between black holes and supernovae, consider subscribing to FactVerse for more explorations of the unknown. And if you have your own theories or questions about primordial black holes, type Ia supernovae, or the mysteries of the universe, share them in the comments. After all, the most exciting discoveries often begin with a single question. Until next time, keep looking up.